We have taking problems from this book of Olympiad problems from 1998. It's got problems and solutions. We're just choosing problems, looking at their solutions, turning them from the informal math into formally verified lean code. And this week the problem is from the Bulgarian Mathematical Olympiad 1998, problem number 8. The polynomials Pn xy for n equals 1, 2, ... are defined by P1 xy equals 1, and P of n plus 1 of x of y is defined recursively as x plus y minus 1 times y plus 1 times P of n x y plus 2 plus y minus y squared times P of n x of y. So we're given that function, and we want to prove that it's symmetric, that P of n of x of y equals P of n of y of x for all x, y, and n. So I've written out the definition of P here. So one difference between this formal version and the informal one is I'm starting at 0 rather than 1. This is n equals 1, 2, ... In the formal land, we like to use natural numbers which start at 0, so I'm just saying that this thing starts at 0, and I'm just shifting it by 1. Shouldn't really make any difference because all that we're doing is n and n plus 1, and we're never subtracting, we're never going back 2 steps or anything like that. So I believe this faithfully transcribes that informal definition up there, x plus y minus 1 times y plus 1 times P of n x y. Oh, it does not. I did do y plus 2 here. Indeed, in the book it is y plus 2. R, right now I'm saying it's just an arbitrary ring. It's possible that during the course of this proof we will find that assumptions are being made about this ring. Often with these problems, it's just sort of implicitly assumed that we're dealing with real numbers, for instance. So we might get to a point in the proof where we have to make some assumption about R, and we'll try to get by with minimum assumptions when we get there. Okay, and the problem statement is for all n, x, and y, P of n x, y equals P of n, y, x. That looks correct. I have the whole proof here informally, and I'm just going to go step by step, translate the lines. Unsurprisingly, the proof is an induction on n. I like the way to do that in lean is like induction n. And that gives us 2 sub-goals, base case and the inductive case. I think for this problem we actually need strong induction, which means the inductive hypothesis needs to be not just the previous n, it needs to be like all previous n. So here it was just plain induction. The inductive hypothesis is only talking about n minus 1. We want that to be like for all m less than n. And the way to do that is strong induction. I forget exactly the syntax for that, so I'm going to go into this other file where I've already done this before. Okay. Indeed, in this case, there's not 2 branches because the 0 case sort of gets rolled into it, because in the 0 case, the inductive hypothesis becomes vacuous, I guess. The inductive hypothesis now has this for all quantifier, for all m less than n. But we have the symmetry condition that we're looking for. And I think we want to now get ourselves into a state where we know that kind of just want it to be n. Stuff that's being asked for next here. We want to be able to assume that n is greater than 2, I think. So I think we need to just discharge the 0 and the 1 cases here. So the way to do that is just cases n. Cases is like weak induction. It's like induction where you don't get the inductive hypothesis. Saying either it's 0 or it's suck of something. So the 0 case, I can probably maybe just ruffle. Yeah, it's definitionally true. Ruffle is just unfolding the definition of P up here. It's if n equals 0, then both sides of this are equal to 1 by this first branch. I'm going to write it like this because we're kind of just like peeling off cases. I'm going to do it again. Okay, this time it's not quite as trivial, but I think we're still going to be able to just kind of unfold definitions. Maybe I can just say like ring. I think I need to import the ring tactic. Ring doesn't do it quite yet. Maybe I can try unfold. Actually, probably I need to assume it's like a commutative ring. Yeah. Okay, cool. As predicted, we needed to add some more assumptions. It's not just any ring, it's a ring where we can commute multiplications. So probably we need to like turn an x times y into a y times x for this to work. I'm gonna maybe write this as a lemma. I'll just call it lemma 1. So I want to prove that P of n plus 1 of xy is equal to x plus y minus 1 times y plus 1 and y plus 2. Function expected at y plus 1 term there's some kind of weird parsing happening here. Oh yeah, of course. Informally, we can write multiplication as just things next to each other, but in lean I have to write it as an asterisk. And that means times. So if we're lucky, I can just say ring here again, and it's not, but it's not. Okay. Okay, so I'm going to need the inductive hypothesis. And I thought I was being smart by like putting this like in its own lemma, but maybe that's just going to be too annoying. I should just do this in line. I'll just call it H1. What am I doing? The first step is like this. That should be too many equal signs. Oh, wait, unfold P just does it. Okay. So maybe this is ruffle. Okay. And then, so I just need to apply the induction hypothesis to each of these applications of the P function. I think wrapping this whole thing in this is just abstraction. I think I just want to put everything in a single calc block here. I think we're going to want to end up applying the induction hypothesis twice, once for n and once for n.suck. And I think I actually want to be working with n.suck in these things here. I'm just going to type out what's over here. Pn minus 1? I can't write that. Oh, there again. Like that? Yeah. This first line was just from the problem statement. That's just the definition of P, and then we apply the induction hypothesis to say that we can switch the arguments these two applications. So, okay, so that's what the informal proof says here, and that's what I'm trying to translate. And like the only tricky thing here is that we're kind of like translating between this n plus 1 and the n in my formal version. Because in the formal version, we have this n.suck. That's like just baking in the assumption that n is greater than 1, so that I know that I can go back 2 steps. And now my hope was that I could just say like ring here. No, actually, I need to apply the inductive hypothesis. So it's like rewrite IH1. That was my hope. By rewrite H1. Right? That worked. And maybe I can do it twice in the same step. No. Well, let's just write out what needs to happen here. We want to now. So it's like I've rewritten second one. I need to rewrite the first instance here. So if I just try to rewrite by IH1, it will hit, well, there is something called nth rewrite, and I can just sort of try on error. Maybe 2, 3, 4. Well, I can be more specific. Oh, of course. There's a problem here that I've like fixed what x and y are. Oh, okay, yeah. We need to revert x and y for our induction. The problem I was running into is that this inductive hypothesis that I have, so we did strong induction so that we get it for all m less than n, but we still only have it for like a fixed x and y. I really want to quantify it so that I have it for all m less than n and for all x and all y. So for that to happen, I need to go up here and say revert x, y, and then they should be inside of the inductive hypothesis. And for this ruffle to work, then I had to like reintroduce x and y. And I guess here also I need to do intros. Yeah, that just pulls the x and the y over to the left. Okay, I need to, I think, once again introduce x and y. Back to what I didn't want to do before, which was ascribe a type to H1 before I try to prove it. So H1 is going to be all x, y, and r. This thing equals this thing. Now the rewrite claims to not actually work. Or it doesn't close the goal. Do I need to just say ruffle after that? No. It rewrites the wrong thing. Okay, so it works when I tell, because now IH1 is quantified by x and y, so I can tell it here which ones to apply to. For this last rewrite, the thing that's left to do is to turn, or maybe I actually didn't, I've got a copy paste error. Maybe? I think what I intended to say here was y plus 2x, and indeed what I intended to say here was also y plus 2x. We want to flip the arguments for both of these terms, and so far we've flipped the argument for the second one, and we need to flip it for the first one here. This x and y plus 2 needs to turn into y plus 2 and x, and so to tell rewrite which one to apply to, I just say x, y plus 2. Awesome. And now I'm pretty confident we can collapse some of this. We can just do both rewrites at once. And I wonder if we even need this first thing. I think we probably do, because we need to unfold. It unfolds. Yeah, we need to unfold the definition of P. But we can at least get rid of this, and that's all. So now that is our first little lemma. Let's transcribe some more of the informal stuff. Note that, okay, this is going to require us to define a little helper function. Note that x plus y minus 1, y plus 1 times p even y plus 2x. This s of n is something we haven't defined yet. S of n, x, y, actually n minus 1. Y plus x plus y minus 1, y plus 1. So I think I'm going to define this s function up here. Okay, I no longer need this. xy plus y squared minus 1 y. Okay, I need to say n here. And I think that defines s. For this note that, for all these like note that things, I just turn them into little inline lemmas. So the second inline lemma is going to be called h2. Oh, right, I need to add a for all there. Okay, and expect proving this will just kind of be like apply h1 or rewrite using h1 and then ring or ruffle or something. Unfold s. I'm a little worried that my h1 is talking. Oh, I think I still need to translate my n's in here. I need to be talking about unstuck, I think. Yeah, so I think I need to be talking about, when it's n minus 1, it needs to be just n. And when it's just n, it needs to be unstuck. And that's going to let us use h1 because h1 talks about unstuck. Oh, yeah, I might be in the realm of confusing myself now. I can at least unfold s. Right. Well, let me just actually try doing this computation here just by hand. Write out the informal definition. So this is the thing we're trying to simplify. A bunch of these things should cancel out. I kind of feel like I should have like Mathematica open or something just to like do all this polynomial arithmetic. Anyway, I was going to factor out an x from this expression. 1 minus x. What happens if I just do ring nf here? Still a lot of stuff. We jump from this thing that talks about p of n plus 1, and then we don't have any p of n plus 1 over here to apply to. Maybe this is just like a trivial thing that I don't even need to use this previous hypothesis for. Maybe I just need to unfold p. I want to unfold this p here so that it goes in terms of p of n. I can write the p of n of suck in terms of p of n, right? Because p is inductive. Yeah, I bet that's it. I bet I just unfold p once. But I can't just do this because then it will unfold all of the p's, and that's not what I want. Is that true? No, I think it just did what I wanted. And then ring nf, and then it's still this really big thing. I was really hoping everything would cancel out. I'm just looking for instances for terms that are like where I can swap the order of these arguments, and maybe that would help things cancel. But for all of these terms, I'm seeing the y part come first. And there is, of course, always the possibility that there is a typo in the book that I'm transcribing from that has happened more than once. And of course, the answer is I should just, actually understand the proof myself. But I am lazy, and I want to be as lazy as possible and just, translate things syntactically when I can get away with it. Since I foresee being stuck at least for a few more minutes, what I'm going to do is git commit, git push, and if anyone following at home wants to, I'll poke around at it while I'm doing this. The link is, in the stream description. Yeah, maybe this is a fun way to noodle. I can say like have equals calc. Okay, what did I type wrong here? P of n. Oh, I did not mean to try to uncurry P there. Okay. So that's just writing out the definition of P. Oh, I'm becoming more convinced that I need to do a different lemma for H1. That I need to get different indices up here. I mean, maybe just unstuck. I'm just looking for things where I can use H1 to rewrite stuff in here. Try H1 is going to let us rewrite something of the form P of n suck. So the things that we have, it's always y plus 2x here. So I guess that's the only possible thing that we could use H1 for here. But there's just no way it's going to help because, well, maybe it will. What happens if we do it? So we have H1 of y plus 2. Let's just call that H3. And I can rewrite, right? That gives us this even bigger term. Try ring. Does ring do it? I mean, it looks like I'm just making things even more and more complicated. I should make sure that H1 is something that's actually true, because I did sorry this up here after I tried futzing with the indices. In the informal proof at this point, we're trying to prove something about n plus 1 in our formal version, n.suck. When we talk about n plus 1, this is the informal proof. That should correspond to n.suck. So this H1 really actually wants to talk about n.suck, which is how I had it before. So I should be able to just uncomment this. Cool. The informal proof n minus 1 should correspond to just n, right? N should correspond to n.suck. P of n goes to n.suck. S of n minus 1 goes to s of n. We're adding 1 to the informal n to get to our formal 1. We need to close this. Okay, right, and this is where I got before, and the problem is that, well, written this way, I can't apply H1 because it's talking about n plus 2, and I'm only dealing with n plus 1 here. Maybe try to make this more readable. Maybe information I can glean from this term that seems to be stuck at. I mean, I wonder if there's somehow do I need to assume that this is more than a commutative ring? I mean, I'm just doing addition and multiplication here. Oh, may have written the definition of S wrong. Let's see, plus 2 here. Changes things. Does it make it work actually? I mean, what I'm trying to do is get this so that like all of the P terms here have the same arguments so that I can like factor them out. X plus 2, y plus 2, x plus 2, y plus 2. But then there's still these two terms, y plus 2x and x, y plus 2. I can apply the inductive hypothesis to swap those arguments, and then maybe ring will just make it go through. Always hoping the ring will just make it work. Just trying to decide which indices to use here. Instead of deleting this, because I'm going to try this again, let's try a version of this with slightly different index and up by 1. I'm a bit confused about why this thing still works here. Okay, let's just start this. So my hope is that rewriting this, so p of x and y plus 2, swap them to y plus 2x, and somehow that will cause these two terms to cancel. IH1 of x, y plus 2. Let's try that. Rewrite IH1 x, y plus 2. Ring? And it just gets bigger. Okay, let's make sure it did what we thought it was going to do. So in the goal here, this and this are the same. I was hoping that would mean somehow they cancel. Apparently not. I am going to call it for the night. Hello. So I think I found the problem from last night. I think it just had to do with, like, remember I had an error in the definition of S. I think I didn't have like one of these plus 2s over here. But then like after I fixed it, I didn't actually try doing the obvious thing down here when I plugged it in. So I think I just need to unfold S, unfold P, and then ring just works. I think that's true. Yeah, great. It was that easy. Like, I scribbled a bunch of algebraic calculations to give myself confidence in that. In the end, all I needed to do was do the obvious thing. And I think, yeah, so it works with both of these cases here. Not sure which one of them I will need going forward, so I'll just leave them both in for now. The only difference between H2 and H2 prime is the index, whether it's n.suck or n.suck. I am going to delete this other calculation thing that is not necessary. Git commit. Get unstuck is my commit message. All right, now we can make forward progress. So the next thing, so H3 is just the symmetry of S. S, M, Y, and R. S of M of X of Y equals S M of Y of X. And this is just going to be applying the inductive hypothesis. Intros M, H, M, X, Y. And then I just plug in those into IH. So IH, M, H, M, X, Y. And then plug that into the unfolded thing. So unfold S, rewrite this. I guess I gotta do inductive hypothesis with y plus 2, x plus 2, and x plus 2, y plus 2. Which way do I want to go? Doesn't really matter. IHM, why doesn't that work? Because I gotta put HM in there. Nice. I do have to unfold S in order to be able to do that rewrite, but that's not surprising. Next step here, I'm being asked to define another helper function called t. Let's hope we don't have a typo this time. T minus 1 x, y. This should, again, just be sort of intros, unfold, and then ring. Ring. Bam! Just put it on one line there. Okay, as before, we will prove that T is also symmetric. I can kind of just copy this H3 thing, I think. And then I think we have to do a different inductive hypothesis here. Just XY, maybe? Okay, cool. We have one more helper function, and then we're done. I think this is just going to follow the same pattern. This one has a few more terms. X. Want to prove that U also is symmetric. Nice. And I think I just have a calculation remaining. The point here is that we're writing p of n plus 2 in terms of these other helper functions, and we know the helper functions are symmetric, so we know that p must be symmetric. I guess I first do need to establish that this equality holds. Okay, I think I'm actually just supposed to just sort of in sequence use these lemmas that I've established. So H1 was the first one, so I can say rewrite H1 x, y, right? Okay, that indeed does apply. And so now the thing that we have is this term, and indeed H2 should exactly match that. Okay, cool. So rewrite H2 of xy. And now what I hope will happen is I think h4 will be the next one that would apply. So h4 will apply to something of the form y minus y squared times p unstuck yx. Do I have something? And I do have a term like that. I have this subterm here, and then I have this other one here, which is the same thing, just sort of reversed with x and y. So that's promising. Rewriting both of those maybe? Or maybe one of them will be for u of x, one of them will be for t. Yeah, I think we might have skipped a step here with u, but I can at least do the one. h4, I think just xy again, right? Nice. Now it almost seems I can do h4yx as well. No, the thing that's missing is rewriting this in terms of u. But I mean, at this point I can just maybe just unfold u and then just do ring and maybe it'll just work. Yeah, awesome. Don't even think about it, just tell the tactic to do it. And now I think we just apply the symmetry things and we're done. So the next step is just to show that, well, it's like just to reverse the x and y in all of these. Let's put this under the quantifiers because I think I want to instantiate it twice. Rewrite p in terms of st and u, and that's just h7 of xy. Next step, apply symmetry to each of these things. Apply rewrite. So symmetry for s was h3. N is less than n plus 2. So let's lt add 1. lt step, okay. And then I want I want h3 xy, h3 n h9, n h9 xy. Doesn't work. Oh, I just wrote it wrong here. I meant to say s of n yx. Nice. Now I switch the y and the x in t. That's going to be similar, except instead of h3, it's h5. Cool. And similar for u. And then instead of h5, it's h6. Okay. And now we're going to apply h7 again in the other order to pack this back up. Yx. So it's like h7 of yx, but I have to apply symmetry to it. I'm not hitting the right parenthesis button. Come on. Yes. Okay. And that's actually what we want to prove. So we're done. Get rid of that sorry. There might still be a sorry up above, but it should be easy to get rid of that. I think actually it's in the branch that we didn't use. So I think I just delete it. Yeah, I had this h1 prime and h2 prime, but I did not end up using those. There we go. It works. There's no sorry in it. In the future, I would like to have a nice juicy animation, like proof completed and like confetti goes everywhere. Because we won. We beat the boss here. Thanks for watching.